In the autumn of 1995, a spacecraft crossed the boundary into the Jupiter system and began falling, slowly and in silence, toward the largest planet in the solar system. It had been traveling for 6 years. Around it, in every direction, was the dark between the worlds, not the soft dark of a room at night, but a cold so absolute and a distance so great that the nearest star would have looked, from there, like a point of frost on black glass. The spacecraft was called Galileo, and among the instruments mounted along its frame was a magnetometer, a device for reading magnetic fields the way a compass reads the pull of the north, sensing not just strength but direction, and the slow way both things changed across space and time. Jupiter announced itself long before the spacecraft arrived. Its magnetic field, the largest planetary field in the solar system, reaches outward past the orbits of its innermost moons and beyond. In the dark ahead of Galileo, that field filled space invisibly, pulsing and rotating with the planet. And as the spacecraft drew close and began its series of passes near the moons, the magnetometer began returning readings that did not fit the field alone. Near Europa, the numbers were wrong, not dramatically wrong, not the kind of wrong that is obvious at a glance, but wrong in the way that careful instruments trained on careful measurements register something they were not expecting, a faint, steady deviation, small enough that it took time to trust it, and then more time to understand what it meant. Something beneath the surface of Europa was responding to Jupiter's field, something conductive, something large. The outer solar system is a cold place. At the distance where Jupiter orbits, the sun is a bright star, rather than a warm one, its light arriving with only about 4% of the intensity it carries at Earth. The moons of Jupiter sit in perpetual cold, their surfaces reaching temperatures of -160 degrees Celsius and lower. Rock and ice in the deep outer solar system do not move, do not warm, do not change in any way the eye would record. At human scales, they seem as still and as finished as the images returned by cameras, static spheres, airless, frozen, silent. That was the picture before the magnetometer readings from Europa, and the readings said the picture was incomplete. The mechanism by which the magnetometer detected what lay beneath took years to work out and several years more to fully trust. But its foundations are simple. Jupiter's magnetic field is tilted relative to the planet's rotation axis by about 10 degrees, a significant lean, enough to matter. As Jupiter spins, its tilted field sweeps through the surrounding space and through the interiors of its moons in a slow, continuous rotation, changing its orientation from any fixed point every 10 hours, which is the time it takes Jupiter to complete one full turn. To a moon sitting within that field, the field appears to rock gently back and forth, like a lantern swaying in a long, slow wind. If the interior of a moon is electrically inert, rock, ice, or cold, dry material that does not carry a current, the rotating field passes through it and continues without leaving a trace. The moon makes no reply. But if the interior contains something that can carry an electric current, salty water for instance, in which dissolved minerals break apart into ions that move freely through the liquid, the changing field induces a flow of charge within that conducting layer, and that flow generates its own magnetic field, a secondary field oriented to oppose the one that produced it, the way an echo answers a call. The two fields together, the planet's and the moon's response, produce a combined signal that a sensitive magnetometer can read and, given careful analysis, untangle. That secondary field, faint against Jupiter's enormous primary, was exactly what Galileo had been measuring near Europa. To produce the signal the magnetometer recorded, The conducting layer would need to be substantial, not a thin film of brine sitting near the surface, but something deep and broad, a body of liquid reaching tens of kilometers thick or more. The signal also implied that the liquid was salty, rich enough in dissolved minerals to carry the induced current that the data required. And the signal persisted, pass after pass, orbit after orbit, as Galileo continued its years-long survey of the Jupiter system. The anomaly was there. Europa was responding to Jupiter's field. Something within it was conducting. The scientific case took years to build and was not made from the magnetometer alone. Galileo's cameras were returning images of Europa's surface throughout those same years, and what they showed deepened the story rather than complicating it. Europa's surface was nearly free of large impact craters. On a world billions of years old, bombarded by the same interplanetary debris that scarred the Moon and Mars and the other solid bodies of the solar system, this smoothness was not ordinary. Craters accumulate over time. The older and more geologically quiet a surface is, the more craters it carries, each one a preserved record of a collision that happened and was not erased. Europa's surface had very few of these records. It was being erased. Something beneath the ice was renewing it, wiping the slate, filling old scars and writing new features in their place. The ice was young because it was not sitting still. It was a surface in motion, fed from below, reshaped by forces working in the dark beneath it. And those forces, the images strongly suggested, included warm or liquid water. The ice of Europa, pale and fractured and laced with long reddish-brown lines, was not the stable, ancient rind of a dead world. It was a lid, a thin covering. Below it, if the magnetometer data were right, was an ocean. The idea that liquid water could survive billions of years inside a moon so far from the sun required an explanation, and the explanation had been proposed years before Galileo arrived. Proposed, in fact, just before another spacecraft revealed a fact that made the proposal feel much more urgent. In 1979, 3 scientists published a short paper in the journal Geophysical Research Letters. Their names were Stanton Peele, Patrick Casson, and Ray Reynolds, and what they had worked out was this: a moon forced into an elliptical orbit by the gravitational competition of neighboring bodies does not simply circle its planet in peaceful silence. It is squeezed. As it moves closer to its planet at one point in its orbit and farther away at another, the gravitational pull on it changes, and the changing pull deforms its shape, stretching it slightly toward the planet when close, releasing it slightly when far. This constant flexing, billions of times over billions of years, generates heat in the same way that a metal wire bent back and forth by hand grows warm in the fingers. The process has a name. It is called tidal heating. Peele, Casson, and Reynolds calculated that tidal heating acting on Io, the innermost of Jupiter's large moons, locked into a gravitational resonance with Europa and Ganymede that keeps its orbit slightly elliptical, should be sufficient to melt rock. They predicted active volcanism. And within days of the paper's publication, images from Voyager 1, passing through the Jupiter system on its own trajectory, returned the first photographs of active volcanoes erupting on another world. Io's surface was alive with them, sulfurous and violent, and precisely as the paper had described. It was among the more striking moments in the history of prediction and observation. The theory and the evidence arrived almost simultaneously from 2 entirely different directions, and they agreed. And if tidal heating could melt rock in Io, it could melt ice in Europa. The orbital geometry that generates Io's volcanism acts on Europa as well, less intensely, since Europa is farther from Jupiter, but the mechanism is the same. A slightly elliptical orbit maintained by the gravitational competition of neighboring moons, producing a continuous cyclic deformation, producing heat. Not enough heat to boil water or dissolve rock, but enough if the ice shell is thick enough to insulate the heat that accumulates below it, to keep a deep ocean liquid across billions of years. The ocean did not need the sun, it had something older and more reliable: gravity, the pull of a planet on a moon, the answering pull of neighboring moons adjusting that orbit, and the slow warmth generated by the incompleteness of every ellipse. In the cold dark far from the star, the ocean was kept alive by mechanics alone. Galileo continued its passes through the Jupiter system for years beyond its original mission, instrument by instrument, flyby by flyby, building the case that what lay beneath Europa's ice was real. The magnetometer data accumulated and were reanalyzed. The camera images revealed more of the surface geology. The picture that assembled itself across those years was not a picture of a static frozen moon. It was a picture of a world in process, one whose surface was shaped by the ocean beneath it, and whose interior carried more water than all of Earth's seas combined, held liquid not by proximity to the sun, but by the inexhaustible patience of gravitational mechanics. Then, in 2005, a different spacecraft gave the argument something new. Cassini had been in the Saturn system for less than a year when it made a pass near Enceladus, a small moon of Saturn, smaller than the state of Arizona, almost perfectly white, its surface one of the most reflective in the solar system. Saturn's inner moons were not expected to be geologically interesting. They were thought to be cold and old and quiet. What Cassini observed during that first close pass disrupted the expectation entirely. The south polar region of Enceladus was warm. Not warm in any way that the human body would recognize. The surface temperature, even there, was around -93 degrees Celsius, still cold enough to make any ordinary material brittle. But it was warm relative to the surrounding polar terrain, which reached the temperatures expected for a body so far from the sun, closer to -200 degrees. The south pole of Enceladus glowed in infrared against its own surroundings. And from 4 long fractures crossing that warm terrain, fractures that had already been photographed and noted as unusual but not yet understood, material was rising into space. The fractures stretched roughly parallel to one another across the south polar surface, each one about 130 kilometers in length, dark and warm against the bright surrounding ice. Above them, visible in Cassini's cameras when the angle of the light was right, when the sun was behind the moon and the scattered light caught the particles in the plumes, curtains of ice crystals and water vapor rose hundreds of kilometers from the surface into the black above. The geysers of Enceladus, they became one of the defining images of the outer solar system, pale against the dark, their material drifting upward and outward, seeding the broad faint ring that Saturn carries at the distance of Enceladus's orbit. The ring had been known for decades before Cassini arrived. Its source had not been certain. Cassini made the source certain: the ocean hidden beneath Enceladus's south pole, venting continuously through 4 fractures in the ice. What Cassini measured in those plumes reshaped the question of what ocean worlds might contain and what they might be capable of sustaining. The spacecraft flew through the ejected material and tasted it with instruments designed to count and identify molecules. The plumes were not simply water vapor. They carried with them salts, particles of silica, just a few billionths of a meter across, carbon dioxide, methane, molecular hydrogen, and complex organic molecules large enough to be the building blocks of biological chemistry. The ocean was not a cold, inert pool. It was chemically active, churning with the products of reactions between water and rock at temperatures that no light from the sun had ever reached. The silica particles were among the most specific pieces of evidence. Silica grains of the size Cassini measured can only form in a particular way, in warm alkaline water saturated with dissolved silica that then cools relatively quickly. The temperature required is around 90 degrees Celsius or above. The alkalinity required is significant, a pH well above neutral. These are the conditions produced by a specific kind of chemical reaction that happens when seawater moves through iron-rich and magnesium-rich rock at depth, releasing heat and raising the pH and dissolving silica from the rock itself. The grains forming in that environment are tiny and specific, and the ones Cassini caught in the plume of Enceladus were exactly that size and composition. The ocean floor of Enceladus, the data said, was hot. Not everywhere, perhaps, but in places hot enough to drive chemistry of the kind that requires both warmth and rock and water in sustained contact. The silica grains drifted upward through kilometers of cold ocean, and then through kilometers of ice, and then out into space and into the path of a spacecraft. They had come from the bottom of the sea. Each piece of evidence that accumulated around Europa and Enceladus strengthened not just the case for those two worlds, but the framework for thinking about what could exist elsewhere in the cold outer solar system. If tidal heating could sustain a liquid ocean beneath Europa's ice and drive active geology at the seafloor of Enceladus, then the mechanism was not a rarity. Any moon locked in the right orbital relationship with a large enough planet and neighboring moons might be generating heat in its interior. Any moon with sufficient water ice in its bulk composition might have turned some of that ice to liquid and kept it liquid for as long as the orbital mechanics persisted. The outer solar system, it turned out, contained many such moons. In 2015, a team of researchers led by Joachim Saar published an analysis of observations made with the Hubble Space Telescope. Observations of Ganymede, the largest moon in the solar system, a moon larger than the planet Mercury, orbiting Jupiter in a gravitational resonance with Europa and Io as the outermost of the three. Ganymede is the only moon in the solar system known to generate its own magnetic field, produced by convection in a metallic core that resembles in its basic structure the mechanism by which Earth generates its own field. At its poles, that magnetic field interacts with charged particles in Jupiter's enormous magnetosphere to produce auroras, ribbons of ultraviolet light glowing at the north and south poles, the light emitted when particles from Jupiter's radiation belt collide with Ganymede's thin atmosphere. Those auroral ribbons were the measurement. As Jupiter's magnetic field rotates, tilted as it is, rocking back and forth relative to Ganymede every 10 hours, the auroral bands should rock with it, shifting north and south in response to the changing field. The expected shift, given the magnetic geometry of the system, was about 6 degrees. What Saar and his team measured was about 2 degrees. The auroral bands were not moving as far as they should. Something was dampening their response. Something was absorbing the change in Jupiter's field before it fully reached Ganymede's core and altered the aurora. The best explanation, the one that fit the data and no other reasonable hypothesis did, was a layer of electrically conducting fluid between Ganymede's surface and its core, a layer thick and salty enough to generate an induced magnetic field of its own, opposing Jupiter's rotating influence and reducing the motion of the auroral bands from the expected 6 degrees to the observed 2. The ocean within Ganymede, the analysis concluded, lay deep between 150 and 250 kilometers beneath the surface, sandwiched within a thick shell of ice rather than resting on the rocky seafloor as Europa's is thought to do. It is, in some respects, a harder ocean to reach, buried under hundreds of kilometers of ice, separated from the rock by layers of ice in a different crystalline phase, cut off from the kind of direct water rock chemistry that drives the geology of Enceladus. But it is an ocean, and it is large, containing, by current estimates, more water than all of Earth's surface oceans combined. The auroral ribbons on Ganymede rocked back and forth by 2 degrees instead of 6, a small motion in a small corner of a distant sky, and what it told the people reading the data was that another ocean was there, waiting in the dark below hundreds of kilometers of ice, old and cold and vast. The ocean worlds of the outer solar system did not announce themselves easily or all at once. They were found through anomalies, a magnetometer reading that was slightly wrong, a plume of material rising above a fracture that should have been frozen, auroral bands moving too little. They were found because the instruments were sensitive enough to detect them, and because the theoretical framework existed to interpret what the instruments were saying. And the theoretical framework had been built across decades of careful work, not by grand moments of sudden understanding, but by a succession of careful papers, careful observations, careful recalculations that each moved the picture one small step forward. The magnetometer on Galileo was measuring fields too faint to feel, in a region of space so far from any human hand that the signal it sent home took minutes to travel at the speed of light. It was reading the ocean by reading the field it generated in response to Jupiter's invisible rotation, the way a physician hears a heart through the wall of a chest, not the thing itself, but the field it casts into the surrounding space, legible to the instrument trained to listen for it. Jupiter's magnetic field rotated, as it always has, with the 10-hour spin of the planet. The planet spins as it has for 4.5 billion years. The moons orbit in their resonances, the orbits slightly elliptical, the ellipticities maintained by the gravitational pushing and pulling of neighbors. The interiors flex, the heat accumulates, the ice melts from below, the oceans hold. This is a story about a very long time. The ocean beneath Europa's ice has likely been liquid for hundreds of millions of years, possibly longer. Enceladus's ocean may be sustained by heat generated just as continuously, the tidal flexing of the moon as ceaseless as the orbital mechanics that drive it. The warmth that sustains these hidden seas is not stored. It is continuously generated, the product of a process that does not run down because the orbital dynamics that drive it are maintained by the gravitational architecture of the whole Jupiter system, the whole Saturn system, built into the deep structure of how these planetary families are organized. In the cold and the dark, far from the light and warmth of the sun, these oceans have been sitting in the dark for longer than complex life has existed on Earth. They have been responding to their planet's fields, reacting with their rocky floors, holding heat from tidal friction, cycling water and minerals and chemistry across depths that no light has ever reached. They have been doing this quietly, in the dark, without witness, for a span of time that the mind reaches toward and then releases without fully grasping. What Galileo's magnetometer began to read in 1995 was not a new fact that came into being when the instrument arrived. The ocean was already there. It had been there before the spacecraft was built, before the theory of tidal heating was written down, before anyone had conceived of looking for it. It had been there before the first telescope was pointed at the sky. It had been there, in all likelihood, before there were any eyes at all in the solar system to fail to see it. The instruments found it because the instruments were looking in the right way, trained on the right things, with a theoretical framework developed carefully enough to know what the anomalies meant. The science moved forward, not with a leap, but with accumulation. Readings and rereadings, papers and responses, detections and confirmations, across years and decades. The picture assembled slowly, the way a long exposure photograph assembles in light, detail by detail, the image deepening as the evidence collected. What the instruments found at the end of that long patient accumulation was that the cold outer solar system contains more liquid water than the warm inner one, that the surfaces of the icy moons are not the whole story, that beneath the ice, beneath the pale fractured plains of Europa, beneath the bright south polar terrain of Enceladus with its long warm fractures, beneath the ancient cratered face of Ganymede with its ribbon auroras shifting 2 degrees instead of 6, there are seas, deep, dark, mineral-rich, and old. The tidal heating that sustains them is not a temporary condition or a local accident. It is a structural feature of how planetary systems organize themselves, gravity distributing itself through resonant orbital families, the push and pull of neighboring masses maintaining slight orbital ellipticities, the ellipticities generating heat, the heat melting ice, the ice becoming ocean. As long as the orbital mechanics hold, as long as the resonances are maintained, as long as the planets turn and the moons orbit, and gravity does what gravity has always done, the heat continues and the oceans remain. The sun warms the surface of the earth, and with that warmth sustains nearly everything that moves and grows on the planet's surface. But at the edge of the solar system, in the vast cold dark, where sunlight is a distant and feeble thing, a different engine runs. It runs on gravity. It runs on the slow and continuous flexing of rock and ice under the pull of planets and the cross-pull of orbital neighbors. It runs silently and without interruption and without requiring anything from the star at the center of the system. Below the ice of Europa, the ocean moves in currents shaped by the same tidal forces that flex the crust above it. Below the south pole of Enceladus, the ocean presses against the base of the ice shell and forces its way out through fractures, carrying with it the chemistry of the seafloor, the products of hot water and rock and time. Below the deep layered ice of Ganymede, in the quiet sandwiched between layers of frozen water at pressures the surface knows nothing of, the ocean waits, old and still and vast. Gravity does not rest. The planet turns, the moons orbit in their resonances, as they have for billions of years and will continue to do for billions more, their interiors flexing, the heat moving slowly upward through rock and ice, the oceans held in place by a warmth that needs no sun and follows no season, and has persisted in the dark across a span of time so deep and slow and complete that it asks nothing of the mind except to rest against it and let it continue. The ice drifts, the heat rises, the ocean holds, in the dark and the cold and the silence sustained by gravity alone, as old and as patient and as quiet as the long turning of the worlds themselves. From close orbit, Europa is nearly featureless in the way that old things sometimes are, not because nothing has happened to it, but because what happened kept happening, smoothing and renewing, filling in the scars before they could deepen. The great craters that mark every other solid surface in the solar system are almost entirely absent here. Where they should be, there is only pale and fractured ice, crossed by lines so fine and numerous they resemble the surface of a cracked eggshell held up to light. The moon is small, a little smaller than Earth's own moon, and from a certain distance it looks almost featureless and still. But nothing about it is still. The ice is moving, not quickly, not in any way that could be watched in real time, but over the long count of years and centuries, the surface is in continuous slow motion, driven by forces that originate deep below. What looks like a quiet white sphere is in fact the uppermost face of a geological system in constant operation, cracking, flowing, refreezing, renewing itself from a source of heat and fluid buried far out of sight. The smoothness is not peace, it is evidence. The first thing to notice approaching from above is the absence of large craters. On a geologically dead world, on a moon with no internal heat, no mobile interior, craters accumulate over billions of years like scars on still skin. The older the world, the more it carries. Europa is old, over 4 billion years, and it has been struck by enough debris to leave a surface riddled with scars, if those scars could persist. They do not persist. The surface is young, geologically speaking, estimated at no more than 100 million years old at most, and in many places far younger. Whatever hits the ice is eventually erased. The surface turns over. Between the great smooth plains and the pale fractured regions, a second feature draws attention. Pairs of low ridges, each flanking a narrow trough, run across the surface in long parallel lines. Some extend for thousands of kilometers. They curve gently with the curvature of the moon itself, so vast they cannot be seen in their full length from any single point above the surface. From orbit they look like shallow folds in the ice, raised slightly on either side of a central groove, running off toward the horizon until they vanish in the distance. They are among the most prevalent geological structures on the whole moon. Wherever the instruments looked, the double ridges were there. Understanding how they form requires going inward, pressing through the ice, down past the surface layers, into the interior where Europa's heat and water do their slow work. The ice shell here is not a uniform rigid plate. It is layered, and in some places fractured all the way through, and beneath it, perhaps 15 or 20 miles below the outermost surface, or perhaps deeper in the colder, more ancient regions, there is water. Not a thin film, not a pocket or a lens. A global ocean, dark and vast, unbroken beneath the ice, from one side of the moon to the other. The depth of that ocean is estimated at around 60 miles, though the true figure is still debated and the instruments needed to settle it have not yet returned their data. But even the lower estimates place the volume of Europa's subsurface ocean at roughly twice the volume of all the water in all of Earth's oceans combined. Beneath a crust of ice over a world smaller than Earth's moon, there is more liquid water than exists anywhere on the surface of the only planet known to bear it abundantly. That number is not meant to impress. It is simply the scale of the thing, stated plainly, and the plain statement is enough. The ocean sits in the dark. No sunlight has ever reached it. No wave has ever broken at its surface, because it has no surface in any usual sense, only the underside of the ice above and the rocky seafloor below, and between them the slow cold weight of miles of salt water pressing in all directions at once. The temperature near the top of the ocean, just beneath the ice, is close to freezing. At the bottom, where the water meets the rock, it may be warmer, though by how much is not yet known, and the question of what happens at that rocky interface sits at the center of many of the most important discussions about Europa's potential for life. For now, the ocean is the subject, not the floor. The water is salty. Magnetic measurements taken by a spacecraft passing close to Europa's surface registered a secondary magnetic field being induced in the moon's interior in response to Jupiter's vast rotating magnetic field, a response that requires a conducting layer within the moon and whose characteristics match a layer of electrically conductive salt water rather than solid rock or fresh ice. The salinity suggested by those measurements is comparable to that of Earth's seawater and may in places be higher. The ocean is not pure. It carries dissolved minerals, and on its upper surface, where it meets or approaches the ice, those minerals leave traces. The reddish-brown material that streaks Europa's ridges and plains is one of the moon's most debated features. It follows the fracture lines, concentrates in the chaos regions, and stains the ridges wherever they run. From orbit, it looks like rust or dried blood, or the color that certain salt flats turn in low light. The leading interpretation is that it consists of salts, magnesium sulfate, sodium chloride, possibly sulfuric acid, irradiated by energetic particles from Jupiter's radiation belts into compounds that turn brown, carried upward from the ocean below, and deposited at or near the surface. The chemistry is complex and not fully settled, but the color is a signature of the ocean's composition, written on the ice in the only way the ocean can write anything, by sending its material up through the shell when the shell cracks open. The double ridges are where that process can be followed most closely. Each ridge consists of two raised walls running in parallel, flanking a narrow central trough, and for a long time, their origin was not well understood. The ice shell below a ridge is being flexed continuously, pulled and compressed by the tidal forces that Jupiter's enormous gravity exerts on the moon as it traces its slightly elliptical orbit. That ellipse is not an accident. Europa orbits in a gravitational relationship with its neighbor moons, Io and Ganymede, completing 4 circuits for every one that Ganymede completes, and in this rhythm, the orbits of all 3 are kept slightly off circle. A perfectly circular orbit would bring Europa to the same distance from Jupiter at every point along its path, and the tidal forces would be steady and unchanging. The slight ellipse means the distance varies. Jupiter's pull strengthens as Europa draws closer, then eases as it swings away, and the moon flexes in response, its shape changing minutely but continuously, the ice cracking and closing, the interior stirred by the friction that flexing generates. The heat that flexing produces is estimated at between 1/10 of a terawatt and several terawatts, a range wide enough to leave real uncertainty about the moon's internal temperature, but certain in its lower limit to mean that Europa is not frozen through. Something keeps the water liquid. The orbital mechanics pass down through the gravitational cascade, linking Europa to its siblings and to Jupiter are the engine. In a fracture opened by that flexing, briny water from below can be drawn upward. The water rises into the crack, and where it meets the cold ice above, it freezes against the walls. Over many tidal cycles, years, centuries, the ice that builds along the fracture walls accumulates and pushes outward, raising the flanking ridges. The trough between them is the original fracture, still faintly open or refrozen at the surface, and the ridges on either side are the accumulated product of many episodes of water rising, freezing, and building. A study drawing on radar observations of similar features in Greenland's ice sheet, where meltwater refreezes in fractures and creates structures remarkably similar to Europa's double ridges, gave this mechanism real physical grounding. The comparison is a close one. The scale is different, and the cold is different. In Greenland's water comes from above rather than below. But the mechanical process of water entering a fracture and freezing outward is the same, and what it produces matches what the spacecraft cameras recorded across Europa's surface. The chaos terrain tells a different story about the same underlying ocean. In regions like Connemara Chaos, the surface ice has broken into plates of varying sizes, some as large as a city block, some larger, that have been tilted, shifted, rotated, and then frozen in their new positions, like the pieces of a shattered tile floor, rearranged by an unseen hand. The blocks still carry the ridge and trough patterns of the pre-disruption surface, and when researchers trace those patterns from block to block, the original arrangement could be partially reconstructed. In some cases, the blocks could be fitted back together like puzzle pieces, their edges matching, their surface markings aligning, demonstrating that they were once continuous ice that later broke apart and drifted. What disrupted them is warmth. Either liquid water or a lens of warm, soft ice rising from below destabilized the overlying crust. The rigid surface plates lost their footing and drifted in the disrupted material, then refroze in the positions they happened to occupy when the warmth subsided. The result is the chaos terrain, a region of geological memory, the record of a moment when the ocean's heat worked all the way to the surface, recorded in the tilted blocks and the dark matrix material that fills the space between them. That matrix material is almost certainly refrozen ocean water, rich in the same salts that color the ridges, a direct delivery of the ocean's substance to the top of the ice shell. The chaos regions and the double ridges are not isolated features. They cover most of Europa's surface, intersecting and overprinting each other, the older systems cut through by younger ones, the younger ones fading and being buried in turn. The surface is a palimpsest, a document written over and over on the same material, the oldest writing almost gone, the newest still fading. Reading it requires identifying what was laid down first and what came after, and doing that across a surface that has been continuously reworked over millions of years is a slow and careful task. The ice shell is not a fixed thickness everywhere. In the chaos terrain, where warm material rose close to the surface, the shell may locally thin to just a few miles or even less in the most active regions. Over the older and colder plains, the shell may thicken to 10 or 15 miles or more. The total depth of ice separating the ocean from space varies across the moon, and that variation is itself a record of where the interior has been most active, where the heat flux from the tidal engine has been greatest, where the ocean has most recently pressed against the underside of its roof. Somewhere beneath the surface of Connemara Chaos, as the blocks were drifting and the matrix was refreezing, the ocean was doing what it has done for billions of years, moving slowly in the dark, its currents driven by whatever heat exists at its floor, its chemistry evolving in whatever reactions occur. Where the water meets the rock, the ocean does not know about the surface above it. It has no awareness of the ridges being built at the fracture edges, or the chaos terrain recording its warmth in tilted blocks. It simply persists, old and dark and continuous, the largest single reservoir of liquid water in the known solar system, moving through its slow cycles in a place where no light has ever been. The reddish staining along the ridges points toward that ocean's composition, but for a long time the staining was observed and the source material debated without a clear resolution. The problem is that Europa's surface is also bombarded by energetic particles and charged particles trapped in Jupiter's enormous radiation belts, the same magnetic environment that made the magnetic induction measurements possible. Those particles alter the surface chemistry, transforming the original salt deposits into compounds that would not exist in the ocean itself. What arrives at the surface from below is modified on arrival. Reading the original ocean chemistry from the surface record requires accounting for those transformations, and doing that accurately demands knowing exactly which radiation processes act on which compounds over what timescales. The work is ongoing, and the picture is not yet complete. Still, the reddish material concentrated along the chaos regions and the ridges, the locations where ocean material is most directly delivered, differs in color and composition from the surrounding ice in ways that are consistent with a salty origin. In some regions, the spectral signatures resemble those of magnesium sulfate, in others, sodium chloride. In the most heavily irradiated zones near the equator, complex sulfur compounds dominate. The ocean is speaking through the ice in a language partly scrambled by Jupiter's radiation, and the scientists reading it are working to reconstruct the original message beneath the noise. The question of ice shell thickness matters for a reason beyond geology. A thinner shell is one that might, under the right circumstances, exchange material more freely with the ocean below, one through which the products of whatever chemistry occurs in the ocean might more readily reach the surface, and through which the products of surface radiation chemistry might more readily descend. The surface of Europa is irradiated constantly, and that radiation drives the production of oxidizing compounds, hydrogen peroxide, molecular oxygen in the surface ice. If those compounds can reach the ocean, they represent a potential energy source for any chemistry, biological or otherwise, occurring at the seafloor or in the water column. The thinner the shell, the more efficient that exchange. The thicker the shell, the more isolated the ocean becomes from the energized surface above it. Ice-penetrating radar is the most direct tool for measuring the shell's thickness from orbit. The instrument sends pulses of radio waves downward through the ice, and those pulses reflect from any interface between materials of different densities, the ice surface, any layering within the shell, and potentially the ice-ocean interface at the base of the shell. The depth of the ice-ocean interface can be estimated from the time it takes the reflected signal to return and from the known speed of radio waves in ice. In principle, this gives a direct measurement of shell thickness at each point the spacecraft passes over. Europa Clipper carries exactly such an instrument. The mission launched in October of 2024 on its long arc through the inner solar system and out toward Jupiter, and when it arrives, it will begin the first systematic radar mapping of Europa's ice shell, not from the ground, not from a lander, but from a spacecraft sweeping past in a series of close approaches, each pass gathering a swath of data before the moon recedes again. Nearly 50 individual flybys are planned over the course of the mission, each covering different terrain, different latitudes, different longitudes, each adding another strip to the mosaic being built of the shell's structure. The passes are brief. At closest approach, the spacecraft will come within about 15 miles of the surface, close enough that the instruments can read the ice in fine detail. But the moon's orbital motion means that closest approach lasts only minutes before the spacecraft swings away again and the distance grows. Each flyby is a few minutes of intense measurement, followed by many hours of growing separation, the data recorded, and the instruments listening as the moon falls behind. The picture of the ocean is assembled in narrow strips, one pass at a time, over the course of years. Alongside the radar, a magnetometer will measure the induced magnetic field during each pass, refining the picture of the ocean's conductivity and depth. A mass spectrometer will sample any particles still present in the faint spray of material that has been detected in the space around Europa, a sparse, diffuse cloud of material far less dramatic than Enceladus's great geysers, but perhaps carrying the same kind of chemical information about the ocean it originated in. An imaging spectrometer will map the surface composition in detail, identifying the distribution of salts and organic compounds, and ice phases across the whole moon in a resolution and coverage no previous mission achieved. The combined picture from those instruments will answer some questions and sharpen others. The thickness of the ice shell will narrow from a broad range to something more specific. The ocean's salinity and depth will be constrained more tightly. The chaos terrain will be mapped in relation to the radar profile of the ice below it, testing whether the warm material that disrupted the surface corresponded to thinning of the shell. The double ridges will be crossed and recrossed by radar passes, looking for evidence of the brine channels through which water is thought to have built them. Some of the questions will not be answered by this mission. Whether there is life in the ocean below is not something the spacecraft's instruments are designed to definitively detect. That question requires getting closer. Eventually, though on a timescale that is measured in decades rather than years, reaching the surface and drilling down, or finding a natural conduit through which ocean material comes close enough to sample directly. The mission is a necessary step, not a final one. It maps the territory that future missions will need to cross. The ice that covers Europa's ocean is not a barrier in only one direction. Material from the surface can in principle work its way down over geological time, just as material from the ocean works its way up. Near the base of the ice shell, where the ice is warmer and softer, convective overturn may slowly cycle ice downward and bring fresh ice up to replace it. Over millions of years, the surface and the ocean may exchange material through this slow churning, even without direct fractures reaching all the way through. The two environments are in contact over long time, in ways that matter for what chemistry becomes possible in the ocean and what chemical signatures might eventually reach the surface. The ice shell is also a record of the ocean's history in another sense. The layering within the shell, if the radar can resolve it finely enough, preserves information about past episodes of thickening and thinning, past periods of more or less intense tidal heating, past moments when the ice cracked and chaos terrain formed and refroze. Reading that layering is like reading the rings of a tree or the layers of a sediment core, a vertical record of horizontal time. Each layer of ice is a year or a century or a million years of Europa's past, compressed and preserved in the structure of the shell. Below the ice, the ocean has its own layers and its own history, though that history will be much harder to read. The water nearest the ice roof is coldest and most isolated from the rocky seafloor. The water nearest the floor is warmest, and if tidal heating drives any circulation, it may be there that the chemistry most closely resembles the hydrothermal systems of Earth's own deep seafloor. What that chemistry produces, whether it accumulates any complex molecules, whether it has had sufficient time and sufficient ingredients to produce anything organized, those are questions for instruments not yet built, for a mission not yet flown, for a scientific conversation still in its first chapters. For now, the ocean persists beneath the ice in the way that old things persist. Not dramatically, not with any sign of the energy it contains, but steadily and in the dark. The crust above it moves in slow geological choreography, driven by the tidal engine below. The ridges build over centuries at the fracture lines. The chaos terrain forms and refreezes in episodes spaced millions of years apart. The reddish salts accumulate along the active regions, faint markers of the water's presence. And the ice continuously renews itself, burying the old surface under the new, keeping the record short, keeping the moon young in the way that active worlds stay young, not by resisting time, but by working through it, always reforming, always beginning again. Jupiter hangs above all of this in Europa's sky, if sky is the right word for the radiation-drenched vacuum above the ice. It is enormous there, far larger than the moon appears from Earth. its bands of cloud, and its great storm systems visible in clear detail to any eye looking upward. It dominates the sky the way a wall dominates a room. Not threatening, simply present and vast, its gravity the source of everything that moves beneath the ice. The tides that flex the moon, the heat that keeps the water liquid, the orbital resonance that maintains the elliptical path, all of it traces back to that immense neighboring presence, so large it is almost a failed star, warm enough in its interior to radiate more heat than it receives from the sun, holding its moons in an embrace whose pressure over billions of years has turned the inside of the smallest of them into a furnace of volcanic fire, and the next one out into a hidden sea. The pull of Jupiter on Europa changes by small amounts as the moon moves through its orbit. The difference between the force at Europa's near side and the force at its far side is tiny by any ordinary measure, but the moon is not an ordinary measure. It is a solid body 4 times as wide as the largest mountains on Earth, and even tiny differential forces applied to something of that size create stresses that crack and flex the crust. The cracking follows preferred directions, the orientations where tidal stress is greatest, and then the cracking persists because the fracture is a weakness that future cycles will reopen and work. The ridge systems, the longest of which extend for thousands of kilometers, are the record of those preferred cracking directions accumulated over millions of tidal cycles, each cycle adding a small amount to the walls, the geology writing itself, one tidal beat at a time. The ocean does not age in the way a surface ages. It has no craters. It has no exposed rock to weather and erode. Its floor may shift if the interior is warm enough. Its currents may change over long time as the moon's interior evolves, but the ocean itself is simply water, the same water, largely, that has been there since the moon formed and the ice shell condensed above it, cycling slowly through whatever reactions occur at the floor and the base of the ice, neither growing nor shrinking in any significant way on the timescales that the surface geology records. It is old, and it is continuous, and it moves in whatever slow patterns the circulation of a deep, dark, planet-warmed sea follows, when no wind has ever touched its surface, and no sunlight has ever warmed it from above. The spacecraft has begun its journey, far inside the orbit of the asteroid belt, coasting outward on the long curved path that the orbital mechanics allow. It carries its instruments in a quiet transit that will take years to complete. The instruments are off or in low power standby, waiting for the moment when the deep space around them begins to change, when Jupiter's magnetic field grows strong enough to register, when Europa's limb first appears in the guidance cameras as more than a point of light. That moment is years away. The ocean below the ice has no knowledge of what approaches. It does not wait. It simply continues, as it has for billions of years, in the cold and the dark and the quiet. The ice continues its slow work above it. In the chaos regions, the warm material that last disrupted the surface has cooled and the matrix has refrozen, and the blocks have not moved in a very long time. The ridges continue their slow growth along the fracture lines, barely perceptibly, by fractions of a millimeter in a year, but continuously. The reddish salts continue to accumulate where the ice is newest and the fractures most active. The surface turns over by slow degrees, the geological clock running at a pace where a human lifetime would not register as measurable change, where the difference between now and 1,000 years from now would be invisible to any eye passing over the surface from above. The ocean's surface, if the underside of the ice is its surface, moves with the tides, not by the meters of Earth's ocean tides, shaped by the moon's pull on an open sea, but by the movement of the ice floor above the water, flexing in and out as Europa swings around Jupiter. The water responds to that flexing, pressing upward where the ice opens and falling back where it closes, the entire ocean in slow motion in response to gravity from 140,000 miles away. The motion is everywhere at once. There is no one place where the tidal response is greatest and another where it is absent. The whole ocean participates, the whole floor of ice above it, flexing as a single system, driven by the same force at every point. The fractures that reach the ocean are the exceptions, the places where the tidal system is locally extreme, where the ice has cracked all the way through, and the water can rise without the ceiling of ice preventing it. Those fractures are where the ridges build. They are the communication points between the sealed ocean and the world above it. Through them, over millions of years, the chemical composition of the ocean is carried to the surface, deposited, irradiated, altered, and recorded in the reddish staining that streaks the youngest terrain. Europa Clipper will fly through whatever sparse material persists above the surface. The faint halo of particles shed from the ice, the tenuous traces of the moon's nearly absent atmosphere, the diffuse cloud of material that previous missions detected. Each pass through that material gives the mass spectrometer a brief opportunity to register what the surface is releasing. The signal will be faint, the concentrations low, the chemistry complex, and mixed with the products of radiation processing. But each pass adds to the cumulative record, and over the course of nearly 50 flybys across years of operations, the cumulative record will be detailed. The picture will not be complete when the mission ends. It will be better. The thickness of the ice shell will have been measured at hundreds of points across the surface, the ocean's conductivity constrained to a tighter range, the chaos terrain correlated with the radar profile of the ice below it, the double ridge systems traced and measured and partially explained. The questions that the mission was designed to answer will largely have been answered, and the questions that the answers generate will be the starting point for whatever comes after. What comes after is not fully designed yet. It exists as proposals and concepts and scientific discussions, in papers and workshops, in the long institutional process by which a scientific community decides what it most urgently needs to know. The ocean is patient. It does not participate in that process. It simply continues to press against the underside of its ice roof, to carry its dissolved salts slowly through whatever currents exist in its great dark volume, to warm slightly at the floor where the rocky seafloor absorbs whatever heat the tidal engine delivers, to cool slightly at the ceiling where the ice draws the warmth out of the water and carries it up toward the surface of a moon that has been turning quietly in Jupiter's light for 4 billion years. The spacecraft closes its distance to Jupiter by several 100,000 miles each day. Europa is one of 4 large moons in the system. It will eventually map in detail, and the smallest of those 4, the innermost of the Galilean family, the one whose ice is youngest and whose ocean is closest to the surface. Each flyby will shorten the list of things unknown and lengthen the list of things understood, and the ocean below the ice will still be there when the last flyby is complete, dark and continuous, and still neither diminished nor revealed by the instruments passing above it, only better known, more clearly bounded, more precisely mapped in its dimensions, its chemistry, and its slow geological activity. The ridges will still be building. The chaos terrain will still be cooling toward its next disruption, whenever the warm material from below next rises close enough to soften the surface. The reddish salts will still be accumulating at the fracture lines. and the ice will continue to renew itself in the way it has for as long as the ocean has been beneath it, cracking open, delivering the ocean's signature to the surface, refreezing, being buried, and cracking open again, a cycle as regular as breathing, measured not in seconds, but in centuries, and continuing as calmly now as it did before the first spacecraft ever crossed the orbit of Mars. At the south pole of a small bright moon, the ice is too warm. It should not be. Out in the space where Saturn hangs, the cold is deep enough to hold anything still. A surface left alone in that darkness would settle to roughly minus 200 degrees Celsius, cold enough that ice becomes nearly as hard as stone, cold enough that nothing moves, nothing escapes, nothing rises. The south pole of this moon should be the same as any other pole in the outer solar system, featureless, still, ancient and untouched. It is not. When a spacecraft first passed close enough to measure the temperature of the terrain near the South Pole, the numbers that came back did not fit. Across 4 long dark gashes running nearly parallel through the ice, each one stretching for more than 80 miles, the surface registered around minus 93 degrees Celsius. That is still cold by any earthly measure, but against the expected background of minus 200, it is like finding a hearth burning in the middle of a frozen field. Something below was generating heat, something below was warm enough to matter, and the ice above it was carrying that warmth to the surface and releasing it into space. The moon is Enceladus. It is smaller than the state of Arizona in diameter, pale as fresh snow, and among the most reflective bodies in the solar system. It orbits Saturn at a distance of roughly 150,000 miles. Nothing about it, at first glance, suggests anything unusual. It looks like a simple object. It looks like a finished world. Then the plumes began. The spacecraft was Cassini, and in 2005, its cameras caught something no one had expected to see, rising from those 4 warm fractures near the South Pole. Pale curtains of material were climbing from the surface and continuing upward, not falling back, not curling and settling, but rising hundreds of miles into the darkness above the moon, fine and bright against the black. Where sunlight caught them at the right angle, from behind, they appeared as luminous veils. Jets within the broader curtains emerged as individual threads of white. The south pole of Enceladus, quiet and cold on its surface, everywhere else, was erupting in slow and continuous fountains of its own interior. What was rising was water. Not liquid water, not by the time it cleared the surface. The material crystallized instantly into ice grains as it passed through the near vacuum above the moon. But it had been liquid, not far below. The jets and curtains were fed by an ocean, and the ocean was deep enough and warm enough and pressurized enough to drive its water upward through the cracks in its own frozen ceiling and fling it into space. The plumes of Enceladus were the ocean of Enceladus, broadcasting itself outward into the Saturn system and beyond. The 4 fractures have names: Alexandria, Baghdad, Cairo, Damascus, the tiger stripes as they came to be called, running in near parallel lines across the south polar terrain, each one roughly 80 miles long, each one glowing faintly in infrared against the surrounding ice. From above, they look like the marks left by some enormous and patient hand that had pressed 4 grooves into the surface and held them open. They are not precisely fractures in the static sense. They open and close on a rhythm set by the tides that Saturn's gravity pulls through, Enceladus with every orbit, widening slightly as the moon moves nearer, narrowing slightly as it moves away, and with each cycle, the water and vapor and ice crystals move through them, and the plumes pulse with the moon's own orbital breath. The heat those fractures radiate is not trivial. The total heat flow from the South Polar region has been estimated at somewhere between roughly 5 and 16 gigawatts. That is the output of several large power stations, pouring continuously from a feature of ice that should, by any ordinary accounting, be as cold and inert as the rest of the surface. Something far below is generating that energy and sending it upward, and the tiger stripes are simply where it escapes. Cassini did not only photograph the plumes, it flew through them. On multiple passes, the spacecraft dropped close to Enceladus's south pole and allowed the plume material to stream across its instruments, a device called the ion and neutral mass spectrometer, which identifies molecules by measuring how they behave in an electric field, parsed the composition of the plume gas with care. Hans Ritto. What it found was water vapor, as expected, but it found much more. Carbon dioxide was there, and methane, and molecular hydrogen. Complex organic molecules with masses greater than 200 atomic mass units were detected, structures large enough to be the building blocks of more complicated chemistry, or the broken fragments of still larger compounds. A study published in 2018 reported the presence of potential amino acid precursors in the plume material, molecules that on Earth are the raw ingredients for proteins. The ocean below was speaking. Every gram of plume material that passed through Cassini's instruments was a sample from a hidden sea, carried upward through miles of ice and delivered directly to a spacecraft that happened to be passing overhead. No drilling, no landing, the ocean was doing the work itself. Among the components Cassini measured, one type stood apart from the rest in what it implied. Mixed through the plume material were particles of silica, silicon dioxide, in grains between 2 and 8 nanometers across. At that size, they are far too small to see. They are smaller than most viruses. They are so small that the right way to measure them is not in any ordinary unit of length, but by how they scatter light. What matters is not their size alone, but how they can only form. Silica grains of that particular diameter can only assemble when water that has been saturated with dissolved silica cools rapidly from a temperature above roughly 90 degrees Celsius. The water must be warm, it must be alkaline, and it must cool quickly, meaning it must have risen from somewhere hot and reached somewhere cold in a relatively short time. There is only one setting in which all those conditions come together naturally. That setting is a hydrothermal vent, a place on the floor of an ocean where hot water circulates through fractured rock, dissolves minerals from it, and emerges enriched with those minerals into the colder water above. The silica grains were formed at the bottom of Enceladus's ocean. They were formed in hot, alkaline, mineral-rich water moving through fractured seafloor rock. They then rose through however many miles of ocean above that seafloor, passed through the ice shell, entered the plume, and eventually flew across Cassini's instruments. Each grain was a small, hard record of conditions at the bottom of a sea no human instrument had directly touched. The ocean floor of Enceladus is hot. It is actively exchanging chemistry between water and rock. It is, in the language of planetary science, in contact with its rocky interior. The molecular hydrogen that Cassini measured tells the same story from a different angle. In a 2017 paper, Hunter Waite and colleagues reported that the plume gas contained molecular hydrogen at concentrations between about 0, 4, and 1, 4% by volume. That number means something specific. Molecular hydrogen does not accumulate naturally in large quantities, just from ice melting or ocean water sitting still. It is produced when certain kinds of rock, iron-rich and magnesium-rich rock, of the kind found in a moon's rocky interior, react chemically with liquid water at elevated temperatures. The process is called serpentinization, named for the greenish, scaled appearance of the rock it produces. When water meets these minerals at heat, the minerals are chemically transformed and molecular hydrogen is released as a byproduct. Serpentinization matters for a reason beyond its chemistry. On the floor of Earth's oceans, there are places called lost city vents, not the black smokers of high-temperature volcanic venting, but quieter, more alkaline systems where serpentinization proceeds continuously at moderate temperatures. Around those vents, despite total darkness and no photosynthesis anywhere in their food chains, communities of organisms live and thrive. Methanogens, microorganisms that combine molecular hydrogen with carbon dioxide to produce methane and extract energy from the reaction, are among the primary inhabitants. They do not need sunlight. They do not need organic material from above. They need hydrogen, carbon dioxide, liquid water, and the right minerals. And at the base of Enceladus's ocean, there is evidence for all of those things. The ocean of Enceladus is thought to be slightly alkaline, somewhere between the pH of baking soda and the pH of milk of magnesia, in the range of 9 to 11. It is warm at the seafloor and cooler above. It is an active chemical exchange with the rock below it. It contains organic molecules. It contains molecular hydrogen. It contains the kinds of silica particles that form only in hydrothermal systems. And it vents its contents continuously into space through a set of fractures that open and close with the tides. For life as it is understood, 3 conditions are considered necessary: liquid water, a source of chemical energy that does not depend on sunlight, and organic molecular building blocks. Enceladus's ocean, by the best available evidence, satisfies all 3. That does not mean life is there. It means the conditions for life are there, as far as instruments passing through a plume at high speed can determine. The difference between the conditions for life and life itself is a question that no measurement taken so far has answered. But the conditions are present in a way that very few places in the solar system can match. The plumes themselves continue, day and night, year after year. Saturn's gravity pulls at Enceladus on every orbit, and the tidal flexing keeps the interior warm, and the warm interior keeps the ocean liquid, and the ocean keeps pressing upward through the tiger stripes, and the plumes keep rising. The material they carry feeds Saturn's E-ring, one of the outermost and most diffuse of Saturn's rings, with a continuous supply of fresh ice particles from Enceladus's ocean. The E-ring is, in a real sense, made of ocean. A person looking at Saturn's rings with sufficient magnification, knowing what to look for, would be looking at the substance of a subsurface sea spread across hundreds of thousands of miles of space in a thin, pale arc. The tiger stripes breathe with a frequency set by orbital mechanics. As Enceladus moves through its elliptical path around Saturn, the tidal force varies, strongest at closest approach, weakest at greatest distance. The fractures respond to that variation. When the moon is closest to Saturn, the southern hemisphere is being stretched, and the tiger stripes tend to open slightly wider. When the moon has moved to the far point of its orbit, the stretching relaxes. With each opening and closing, material moves through the fractures, and the plume activity rises and falls. The jets pulse, the curtains thicken and thin. The ocean breathes in a rhythm set by a planet nearly 250,000 miles away, and the plumes carry that rhythm up into space, where a spacecraft can see and measure it. In those pulses, there is a window into the interior. Scientists analyzing the timing and intensity of plume activity across Cassini's many passes have worked backward from what they observed to build a picture of how the fractures behave and how the water moves beneath them. The ice shell through which the plumes travel is estimated at somewhere between a few miles and perhaps 20 miles thick in the South Polar region, thinner there than anywhere else on the moon, worn by the heat rising from below. Below the ice shell, the ocean extends for a depth that is not yet fully determined, perhaps tens of miles, the water warmer near the rocky floor and cooler near the ceiling of ice above. The warmth at the base of that ocean is not a residual heat from ancient times. It is actively generated. The same orbital resonance that forces Enceladus into an elliptical path also prevents its interior from fully cooling. The tidal flexing converts the moon's orbital energy into heat, and that heat sustains the water in its liquid state and drives the circulation that carries silica grains and hydrogen molecules and organic compounds from the rocky floor toward the ice above. The ocean of Enceladus is not a relic, it is a running system. When Cassini passed through the plume on its closest approaches to the South Polar region, the spacecraft was traveling fast. The flyby geometry gave the instruments only minutes to collect data, in some cases a geometry lasting only a few minutes of closest approach before the moon receded and the plume thinned behind the spacecraft. Every measurement was a snapshot taken at speed, a brief and incomplete reading of a vast and continuous chemical conversation happening between the ocean and the rock and the ice above. What those snapshots revealed, assembled across years of repeated flybys, was a coherent picture. The molecular hydrogen pointed to serpentinization. The silica grains pointed to high-temperature hydrothermal circulation. The organic molecules pointed to carbon chemistry at some level of complexity. The alkaline pH inferred from the mineral composition of the plume particles pointed to a water chemistry consistent with what is found at Earth's lost city vents. Each measurement confirmed and extended the others. None of it was easy to interpret. A spacecraft passing through a plume at high speed collects a sample that has already traveled from the seafloor through miles of ocean and miles of ice and miles of space. Each stage of that journey has altered it, stripped away some compounds, degraded others, mixed things that were separated at the source. The instruments doing the measuring were designed for a broad range of scientific tasks and were not specifically engineered to detect biosignatures. The data they returned is a blurred and incomplete record of what the ocean contains. Even so, the picture that emerged was consistent. Even so, the evidence accumulated across multiple instruments, multiple flybys, and multiple years of analysis told the same story in different dialects. The ocean is real. It is salty. It is warm at the bottom. It is in chemical exchange with the rock beneath it. It contains organic molecules. It contains molecular hydrogen. It is actively venting its contents into space. There is a quality to the situation that is, in its own quiet way, quite extraordinary. Enceladus does not require a spacecraft to drill through its ice. It does not require a submarine to descend to its ocean floor. It does not require landing at all. The ocean is already doing the work of delivering its chemistry to the surface and beyond, continuously, through a geological process that has been running for as long as the tidal heating has been running, which may be a very long time. The question of how long Enceladus has maintained its liquid interior is not yet settled. Some models suggest the current period of tidal heating may be relatively recent in the moon's history, a few 100 million years old rather than billions. Others suggest it could be more persistent. But even a few 100 million years is an enormous amount of time for chemistry to proceed, for minerals to dissolve and precipitate, for organic molecules to assemble and break apart, and reassemble in new configurations. Long time, warm water, rock, carbon, hydrogen. These are simple ingredients. They are in different proportions and at different scales the same ingredients that were present on the early Earth. Cassini did not carry instruments designed to detect life. Its mass spectrometer could distinguish molecules by mass and some aspects of their structure, but it could not identify a living cell or read a strand of genetic material or determine whether a complex organic compound had been produced biologically or abiotically. What Cassini found was the conditions for life, not life itself. The distinction is important, and the scientists who published the findings were careful to maintain it. There are many places in the universe where the conditions for life are present and life is not. The conditions for life are necessary, but not sufficient. What Cassini demonstrated is that the question is worth asking seriously. Before 2005, before the plumes were seen, before the tiger stripes were measured, and the plume chemistry was parsed, Enceladus was a small and unremarkable moon in the Saturn system. Interesting perhaps for its high reflectivity, but not a serious candidate for habitability. After the plumes, after the silica grains, after the molecular hydrogen, after the organic compounds, the moon moved into a different category entirely. Not a confirmed habitat, not a confirmed dead world. A place where the question of whether something lives there is a legitimate scientific question with a possible answer. That is a different kind of place than a cold, dead rock. The plumes also have a practical implication. If the question of life in Enceladus's ocean is worth asking, the plumes are the natural place to ask it. A spacecraft flying through the plume would be flying through ocean material. If there are organisms in the ocean, some fraction of the material they produce, cellular components, complex molecules, metabolic byproducts, might be carried upward through the fractures and into the plume. If the right instruments were aboard, and if they were sensitive enough, they might detect a molecular signature of biology without the spacecraft ever entering the ocean, without drilling, without landing on the ice. The ocean is already sending its contents up. A future mission need only catch them and read them carefully. The 2023 Planetary Science Decadal Survey, the document in which the scientific community in the United States sets its priorities for the decade to come, ranked a dedicated Enceladus orbiter and lander as the third highest priority flagship mission. The recommended target for launch is the late 2030s. The instruments being discussed for such a mission include mass spectrometers, more sensitive than those Cassini carried, capable of resolving molecular structures in greater detail, microscopes that could detect individual cells if cells are present, chemical analyzers specifically designed to look for biosignatures, anomalous isotope ratios in carbon compounds, the molecular handedness that distinguishes biological chemistry from abiotic chemistry, the complex polymer structures that life tends to produce and random chemistry tends not to. The mission does not yet exist. It has not yet been funded, built, or launched. It is a recommended priority, a statement that the scientific community believes this question is important enough to spend the resources needed to answer it carefully. If the mission proceeds on the projected timeline, it would not arrive at Enceladus until the 2050s. The answer, if it comes, is still decades away, and it may not come cleanly, since absence of detection in a plume sample is not the same as confirmed absence of life in the ocean below. But the approach is reasonable. The plumes are real. The chemistry they carry is real. The conditions they point to are real. And the idea of a spacecraft passing through those pale curtains of rising water counting molecules one by one, logging their masses and structures and compositions in the few minutes of closest approach. That is not a fantasy. It is the logical next step in a line of investigation that has already transformed a small, pale, unremarkable moon into one of the most carefully studied bodies in the solar system. The tiger stripes run warm and open and continuous across the south pole of Enceladus, as they have been running since before any instrument was there to measure them, as they will continue to run long after the current generation of scientists has finished their analysis and the next generation has taken up the work. Below the fractures, the ocean moves in slow circulation, carrying the chemistry of the seafloor upward toward the ice, where the water passes close to the ceiling of rock, the ceiling of ice rather. Some of it finds its way into cracks and narrow passages and begins to rise. The ice shell above the South Polar region is thinner than anywhere else on the moon, shaped by the heat that has been pressing against it from below for a very long time. In the deepest and warmest passages, the water rises as vapor, and the vapor pushes upward, and the plumes emerge into the cold darkness above the surface, and fan outward, and crystallize, and thin and spread until they become the faint tendrils of material that feed Saturn's E-ring and that Cassini's cameras caught in backlit silhouette against the dark. The silica grains within those plumes formed on the seafloor. They rose through miles of ocean and miles of ice. They traveled hundreds of miles above the surface of a moon before entering the ring system of a planet. Some of them were caught by an instrument on a spacecraft that had traveled for years from Earth to reach this place. Others continued outward, drifting slowly away from Saturn, becoming part of the slow dispersal of matter through interplanetary space. Each one began in hot alkaline water at the base of an ocean no direct instrument has reached. Pure stuff to walk is a record of something happening very far from the surface and very far from the sun, something warm and chemical and continuous, proceeding in the dark at the bottom of a hidden sea on a small moon of Saturn, as it has been proceeding for a span of time long enough that the word ancient does not quite cover it. The plumes rise. They rise in slow pale curtains from the four warm fractures at the South Pole, visible to the right instrument from the right angle, carrying the composition of an ocean upward into space. They do not rise violently. This is not an explosion, not an eruption in the dramatic sense. It is a slow and steady effusion, the pressure of warm water in a confined space, finding the paths of least resistance in the ice above it, and moving steadily and without hurry toward the cold and dark outside. Somewhere in the material rising through those fractures, there may be something more than chemistry. No one knows. The instruments that could tell have not yet been built, or if they have been built, have not yet been sent. What is known is what Cassini returned across its years of flybys: the temperature contrast at the tiger stripes, the composition of the plume gas, the silica grains, the molecular hydrogen, the organic molecules, the inference of a warm alkaline seafloor in continuous chemical exchange with its rocky substrate. What is known is that this small bright moon, orbiting Saturn in the cold outer solar system, far beyond the reach of the sun's warmth, is not cold at its heart. It is alive in the geological sense, at least dynamic, heated, chemically active, venting. Whether it is alive in any other sense is a question the plumes are ready to answer, if the right instrument is there to ask. The curtains of ice crystals drift outward from the South Pole and thin into the Saturn system's cold and quiet dark, carrying with them a chemistry that began on the floor of an ocean none of the instruments have touched, none of the cameras have seen, none of the scientists living today have read completely. They carry it outward and upward, and they do not stop. The moon continues its orbit. Saturn pulls at it on every pass, tightening the ellipse just enough that the interior never fully cools, the ocean never fully freezes, the fractures never fully seal. The heat that keeps the ocean liquid is the heat of an orbital geometry that has been in place for a very long time and shows no sign of changing. The tiger stripes will be warm tomorrow and for centuries after that, and the plumes will continue to rise from them in pale, slow curtains against the dark, and the ocean below will continue to press against the ceiling of ice above it, and the seafloor hydrothermal systems will continue to generate the molecular hydrogen that feeds whatever chemistry proceeds at that depth, and all of this will proceed without interruption, whether or not any instrument is there to measure it. The ocean of Enceladus does not need to be discovered in order to continue. It has been there by the best available estimate for a long time. It will be there for a long time still. In that sense, it is patient in the way that geological things are patient, not waiting for anything, not moving toward any outcome, simply persisting in the conditions that allow it to persist, chemical and warm and liquid in the dark, far below the surface of a moon that from the outside looks like a quiet sphere of ordinary ice. The plumes are the only signal. They rise from the South Pole in their slow pale curtains, visible to the right instrument from the right distance at the right angle, carrying the chemical record of the sea floor up through miles of water and ice into the space above. Any future instrument passing through those curtains would find, as Cassini found, the molecular inventory of an ocean. It would find water and carbon and hydrogen and the particular silica grains that form only in hot alkaline water, far below. It might find, if the instruments are sensitive enough and the conditions below are right, something that abiotic chemistry alone does not typically produce. Until that instrument arrives, the plumes will continue to rise. They will rise through the cold, carrying whatever they carry, seeding the E-ring with the substance of the ocean below, thinning and crystallizing in the space above the moon's south pole, as they have been doing in that cold and unwitnessed dark for a long time before any spacecraft passed close enough to see them, and as they will continue to do, quiet and steady and without interruption, long after the last record of their observation has faded and whatever came next has already happened. The tiger stripes hold their warmth against the surrounding cold. The ocean presses upward through them. The plumes rise and spread, and still, Ganymede is the largest moon in the solar system, larger than the planet Mercury, larger than any other moon circling any other world. It carries within its deep interior more liquid water than all the oceans on Earth combined, and yet not a drop of it has ever touched its surface, or ever will. The ice shell alone descends 500 miles before giving way to anything else. Below that ice, sealed from the universe by a weight of frozen water that would crush anything familiar, there is a sea. It has been there for billions of years. It makes no sound that travels outward. It casts no reflection. And for most of human history, no one knew it existed. The ice at the top of Ganymede's shell is ancient and cold. On the surface, it is marked by long parallel grooves, old impact craters, and pale ridged terrain that records a geological history stretching back to the early solar system. The light that reaches it from the sun is roughly 27 times weaker than the light that reaches Earth, and so the surface is dim, perpetually twilit by comparison, swept by the vast rotating magnetosphere of Jupiter, which dominates the sky the way no planet dominates any moon in the inner solar system. Nothing in that frigid, grooved landscape hints at the water below. The grooves are old, the craters are old, The ice is old. All of it lies quiet above a hidden sea that presses upward from within and will never break through. The depth of that ice is the first thing that sets Ganymede apart from the other ocean worlds. 500 miles of frozen water is not a shell in the ordinary sense. It is a world unto itself, layered like geology. The upper ice grades downward into warmer, softer phases as pressure and the faint residual heat of the moon's interior press inward from below. 500 miles down, the pressure becomes immense. The water molecules themselves begin to lock into new crystalline arrangements, denser than the liquid water above them, and a floor forms at the bottom of the ocean, made not of rock, but of a kind of ice that is heavier than the sea it supports. It is called Ice 6, and below it there is a still denser phase called Ice 7. These are not the ordinary ice of frozen ponds or polar winters. They are exotic, compressed, crystalline matter formed only under pressures thousands of times greater than the weight of Earth's atmosphere, and they sit at the bottom of Ganymede's ocean like a solid floor built from water pressed past its ordinary limits. The ocean rests between two walls of ice. Beneath it, the denser ice phases form the floor. Above it, the ordinary ice shell forms the ceiling. Neither wall is rock. This is what makes Ganymede's ocean different from any ocean on Earth, and different from the hidden seas of the other moons. It is a liquid layer suspended inside a world of ice, touching no silicate rock, drawing no mineral chemistry from a solid sea floor, isolated from the geochemical exchange that stirs and enriches the oceans of the other worlds. Warm water meets cold rock somewhere beneath the ice on other worlds, and something happens there, something chemically rich and possibly consequential for life. At Ganymede, the ocean rests in a layer of its own, bracketed on all sides by frozen water, and what it contains, what it is capable of producing, what slow chemistry unfolds within it, remains an open question that no instrument has yet answered. What betrayed Ganymede's ocean to science was not anything that could be seen. It was a wobble in something invisible. Ganymede has its own magnetic field, the only moon in the solar system that does, and that field produces auroral bands near the poles, ribbons of ultraviolet light that ring the northern and southern polar regions and shift back and forth as Jupiter's enormous magnetic field sweeps across them during each planetary rotation. The prediction was that those auroral bands should rock through an arc of roughly 6 degrees as Jupiter's field, tilted 10 degrees from the moon's rotation axis, tugged at them in its 10-hour sweep. When Joachim Sauer and colleagues used the Hubble Space Telescope to measure the actual motion of those bands, they found the arc was only about 2 degrees. Something inside Ganymede was dampening the effect. A conductive layer beneath the ice, generating its own opposing magnetic signal in response to Jupiter's rotating field, could reduce the rocking to almost exactly what was observed. The most consistent explanation was a deep ocean of salty water, and the ocean's depth, estimated from the physics of the signal, placed it somewhere between 150 and 250 miles beneath the surface. Ganymede's ocean had announced itself through the motion of auroral light. The auroral bands still shift in their slow arcs today, back and forth on a 10-hour period, the rhythm of Jupiter's rotation imprinted on the light at the poles of a moon 770 million miles from where that reading was taken. The shift is small, it is barely detectable, and in its smallness, in its quiet failure to move as much as physics would predict for a frozen solid moon, there is an ocean. That ocean holds more water than all of Earth's surface oceans combined, compressed into a layer roughly 500 miles wide, held at depth by the weight of the ice above and the pressure of the ice below, isolated from rock, isolated from the surface, isolated from the faint light of the distant sun. Whether anything lives within it, whether the chemistry is rich enough, whether there is energy of the right kind moving through that layer of bracketed brine, no one knows. The pressure at the base of the ocean, where Ice 6 begins, reaches several thousand atmospheres. The conditions there have no close analog anywhere on Earth. The best current understanding is that those conditions are unfavorable for the kinds of chemical exchange that seem to drive life elsewhere, but the ocean is so vast and so poorly known that the uncertainty is genuine and broad. Callisto lies just beyond Ganymede, in distance from Jupiter, the fourth of the great moons, and it is in almost every surface feature the opposite of its inner neighbors. Where Ganymede shows grooves and varied terrain, Callisto is covered so uniformly in ancient impact craters that its surface is among the most battered in the solar system. Every square mile of it has been struck repeatedly over billions of years, and the record of those impacts sits undisturbed, unrenewed, unchanged, because nothing from the interior has pushed through the crust in all that time to resurface it. Callisto's face is the face of deep time, left completely alone. The interior of Callisto is just as undisturbed. The other large moons of Jupiter differentiated long ago. Their heavier elements sank toward the core, and their lighter materials rose, producing layered interiors with distinct regions of rock and ice and metal. Callisto never fully differentiated. Its interior is still largely a mixed, undifferentiated mass of rock and ice, neither fully separated nor fully layered, a cold and ancient blend, sitting mostly inert beneath the cratered skin. It generates no magnetic field of its own. It has no auroral bands to measure. Based it gives almost nothing away. And yet when the Galileo spacecraft passed close by Callisto and measured the response of that cold, undifferentiated interior to Jupiter's rotating magnetic field, something unexpected appeared. There was an induced signal. A faint electromagnetic response from within the moon's interior indicated that somewhere inside that ancient rubble of rock and ice there was a layer of electrically conductive fluid, not molten rock, not a metallic core, something more like a brine, a solution carrying dissolved salts, sitting quietly within the mixed interior at a depth that could not be precisely determined. The leading candidates for what that brine contains include magnesium sulfate and compounds of ammonia, which can lower the freezing point of water enough to keep a liquid layer stable within a cold interior that never generated much internal heat. The brine need not be deep or thick or chemically rich. It need only be conductive, and conducting it was, quietly betraying itself to an instrument that measured invisible fields while the moon said nothing else. What kind of ocean this is, or whether ocean is even the right word for it, is unclear. The signal is consistent with a layer of liquid, but the interior of Callisto is not well enough mapped to describe that layer in physical terms. It may be thin, it may be diffuse. It may be spread through fractured rock like water in a sponge, rather than pooled in an open body. The surface gives no indication of any process working below, because nothing from below has reached the surface in so long that whatever internal heat once stirred the moon has long since faded to nearly nothing. Callisto's ocean, if it is an ocean, is old and still, and probably unchanging on any human timescale. It keeps its character behind the oldest, quietest face in the Jovian system. The crater-pocked surface of Callisto stands in almost complete contrast to the active, plume-driven south pole of the much smaller moon Enceladus, or the fractured terrain of Europa, and it stands in contrast to Titan in a different way entirely, because Titan, which orbits Saturn rather than Jupiter, holds not one but two fundamentally different liquid environments stacked within the same body, separated by an ice shell, each of a completely different chemical character, each existing in conditions unlike anything on Earth. Titan is the only body in the solar system besides Earth with stable liquid on its surface. The lakes and seas at Titan's poles are real bodies of liquid, some of them holding more fluid than the Caspian Sea, some small enough to drain dry in a Titan summer. The largest of these, called Kraken Mare, spreads across the North Polar region in a dark, irregular shape visible from spacecraft as a surface that reflects radar and absorbs light in the same way that calm liquid does. But the fluid in these seas is not water. At Titan's surface, the temperature sits around minus 179 degrees Celsius, and at that temperature, water is frozen as hard as granite. What pools on Titan's surface and fills its northern seas is liquid methane, mixed with ethane and dissolved nitrogen, a cold hydrocarbon solution, moving slowly through a landscape of water, ice bedrock, and organic sediment under a sky thick with nitrogen and a haze of complex organic chemistry. The rain that falls on Titan is liquid methane. The rivers that cut channels through the landscape are carved by liquid methane. The deltas that spread near the edges of the seas were built by methane floods, draining toward the lowlands, and the methane evaporates from the sea surface and rises through the thick nitrogen atmosphere and condenses again and falls. It is a hydrological cycle, complete, continuous, operating on the same physical principles as Earth's water cycle, but made of a compound that on Earth is a gas and exists as a liquid only in the cold dark far from the sun. On Titan, the methane does what water does here. It flows, pools, evaporates, rains, and the landscape it shapes is alien in temperature and chemistry, yet strangely familiar in form. The organic chemistry in Titan's atmosphere is the most complex anywhere in the solar system outside of a living world. Ultraviolet light from the sun, filtered by the thick nitrogen haze, drives chemical reactions in the upper atmosphere that produce a constant downfall of organic molecules, particles of tholins, and complex hydrocarbons that drift down through the haze and settle on the surface, coating the dunes and shorelines in a pale reddish-orange sediment. These are not the products of life. They are the products of ultraviolet chemistry acting on methane and nitrogen, the same chemistry that may have operated on early Earth before life began, a kind of natural prebiotic laboratory running on planetary scale. The dunes of Titan are built from this organic sediment, dark and enormous, running parallel across the equatorial regions for hundreds of miles, shaped by slow winds in an atmosphere 2.5 times denser than Earth's, pushing material that arrived from the sky. This is Titan's surface, dark methane seas in the north, vast organic dune fields near the equator, river channels cut through water ice bedrock, a thick orange haze filtering what little sunlight arrives at the top of the atmosphere into a diffuse and permanent twilight at the surface. No direct sunlight reaches Titan's ground. The haze scatters and absorbs it. The surface is lit the way a deeply overcast day is lit, evenly, dimly, the light coming from everywhere and nowhere at once, the sky a uniform pale orange from the ground up, brightening only invisibly at the top of the atmosphere, where the haze gives way to the clear dark of space. Below that surface, below the water ice bedrock, in the ancient geological structures carved by methane and shaped by the slow tides raised by Saturn's gravity, there is a second ocean of a completely different character. Models of Titan's interior, constructed from the way the moon flexes in response to Saturn's tidal pull, suggest that the crust of water ice sits above a deeper layer of liquid water mixed with ammonia, that extends through a global shell somewhere between 50 and 100 miles beneath the surface. Ammonia in water acts as an antifreeze, lowering the temperature at which the mixture freezes well below the freezing point of pure water, and Titan's interior retains enough heat from the decay of radioactive elements in its rock core to keep that ammonia-water mixture liquid at depth. The ocean is warmer than the surface, warmer than the ice above it, kept from freezing by the chemistry of the ammonia and the slow decay of ancient heat sources within the rocky interior below. This ocean has never been directly detected. Its existence is inferred from the way Titan moves, specifically from the measurements of how much the surface shifts during each orbit of Saturn, as tidal forces squeeze and stretch the moon's body. The surface moves more than it would if the interior were entirely solid, and the best explanation for that excess flexibility is a liquid layer decoupled from the outer ice shell, allowing the shell to slip a small amount relative to the interior. The ocean has also been suggested by the magnetic induction data from the Cassini spacecraft, though Titan's thick conducting ionosphere makes interpreting that signal more complex than for the cleaner cases of Europa or Ganymede. What the interior measurements converge on is a picture of a global water ammonia ocean sitting in the cold, dark interior of a moon whose surface is coated in organic chemistry and swept by methane rains. Whether that interior ocean could support life is a genuinely open question, and the honest answer is that no one knows. Ammonia is both a potential antifreeze and a solvent that is chemically different from water in ways that may affect whether it can support the same biochemical processes. The interior is cold and dark, and far from any source of chemical energy comparable to what the hydrothermal systems at Enceladus appear to provide. The ocean may have been active in the early history of the solar system, when Titan's interior was hotter and more geologically alive, and impacts in that early period may have melted the crust temporarily and allowed the surface organic chemistry to mix with the interior ocean, creating a brief window of rich chemistry at a water-organics interface. But the window, if it opened, may have closed long ago. What persists now in the deep interior of Titan is probably cold and dark and still. The surface of Titan is a different kind of invitation. The organic chemistry there is prebiotic chemistry at a scale and complexity that has no equal in the solar system. The tholins raining down from the atmosphere are the same class of compounds that form when ultraviolet light acts on simple organic molecules, and some of the same reactions that led to the first biological molecules on Earth may be running continuously on Titan at the present moment. Though the temperature is so cold, nearly 200 degrees Celsius below the freezing point of water, that any chemistry involving liquid water is entirely absent from the surface. Life as understood on Earth requires liquid water. Titan's surface has none. Pure surface has mods by Tanelbling, but the chemistry there is building towards something, step by step, molecule by molecule, and what that something is and how far it has gotten, and whether any of it has found some other organizing principle that does not require water, no one can say. There is a spacecraft on its way to Titan now. It is called Dragonfly, and it is designed to fly through the thick nitrogen atmosphere using rotors, the way a drone flies on Earth, and to land at multiple locations across the surface to sample the organic chemistry directly, to carry a mass spectrometer capable of identifying amino acids and their precursors, and to sample the dark material of the dune fields and the bright material near impact craters, where the subsurface ice may have been briefly melted and mixed with surface organics, creating pools of warm liquid water and organic molecules sitting in contact with each other for thousands of years before the heat faded and the ice refroze. Those impact melt pools are Titan's most astrobiologically interesting surface features, brief, localized, temporary windows where the two different chemical worlds of the surface and the interior were briefly in contact. If any chemistry of consequence began there, it would have left traces in the crater floors and crater ejecta. Dragonfly will look for those traces directly. The ESA mission called JUICE, the Jupiter Icy Moons Explorer, was launched in the spring of 2023 and is now in cruise toward the Jupiter system, where it will arrive after a journey of about 8 years. Its primary destination is Ganymede, which it will eventually enter orbit around, making it the first spacecraft ever to orbit a moon other than Earth's. Before that orbital insertion, it will perform flybys of Europa and Callisto, and it carries with it a set of instruments designed to read the hidden interiors of all 3 moons in the most detail yet achieved. Its ice-penetrating radar will attempt to sound the depth of Ganymede's ice shell. Its magnetometer will refine the picture of the conductive layers beneath both Ganymede and Callisto. Its imaging spectrometer will map the surface chemistry of all 3 moons across wavelengths the eye cannot see. When JUICE finally settles into orbit around Ganymede, it will circle a moon with an ocean below it that has never been reached, never been sampled, and never been anything other than inferred from the motion of auroral light. The orbital phase is designed to last long enough to produce a detailed global map of the magnetic field, the gravity field, and the surface composition, and to sound the ice shell deeply enough to refine the estimate of where the ocean begins and how thick it is. The first orbital surveys of an icy moon's deep interior are still ahead. The picture that comes back may look very different from the one that exists now, or it may confirm the present model in enough detail to begin planning the next mission, the one that comes after the overview, the one that goes closer to the surface and carries instruments designed not just to detect an ocean, but to say something about what is in it. These 4 moons, Ganymede, Callisto, Titan, and the smaller moons already established as ocean worlds in their own right, are not the same. They are not variations on a single theme. Each of them holds its ocean at a different depth, in a different kind of container, with a different chemistry and a different history. Ganymede's ocean is enormous and isolated within ice, touching no rock, receiving no light, stirred perhaps by nothing more than the slow flexing of tidal forces from a distant giant planet. Callisto's hidden liquid is old and undisturbed, possibly diffuse, possibly thin, a faint electrical whisper from within the most inert-seeming large body in the outer solar system. Titan's deep ocean is cold and laced with ammonia and buried beneath an ice shell whose surface is swept by organic rains and shaped by methane rivers. A moon with 2 different liquid environments separated by 50 miles of ice, neither of them water in its ordinary form. Habitability is not a single condition. It is not a checklist that a world either passes or fails. It is a spectrum shaped by chemistry and depth and heat and time, and the range of ocean worlds in the outer solar system spans that spectrum from one end toward the other without ever filling it completely. The warm, chemically active seafloors implied for some moons represent one kind of possibility. The cold, isolated brine of a partially differentiated interior represents another. The prebiotic chemistry of a thick organic atmosphere and a surface coated in complex molecules represents something further out along the spectrum, something that may not yet have crossed any threshold recognizable as biology, or may never cross it, or may have crossed it long ago in a way that left only the faintest molecular trace. The ice of Ganymede is 500 miles deep. Below it, the ocean sits in its bracketed dark, without rock above or below it, without connection to the surface chemistry of the distant sun. It has been there, in roughly this configuration, since the solar system was young. The tidal forces from Jupiter continue to flex Ganymede's interior on the slow rhythm of its 7-day orbit, and that flexing generates a small but steady warmth that keeps the ocean from freezing entirely, that maintains the liquid layer between the ice walls. Billions of years of this slow mechanical stirring have kept the water liquid and the system stable, and the ocean persists not because of any drama or eruption or visible sign, but because gravity continues to work at the scale of planets and moons with a steadiness that nothing else matches. The ice phases at the base of the ocean are denser than the liquid above them. This means that as the ocean slowly cools over geological time, the water that freezes at the bottom does not float upward as ordinary ice would in an ordinary lake on Earth, but sinks, pressing downward into the high-pressure ice layer below, and the boundary between ocean and floor stays stable, and the ocean does not drain away or crystallize from the bottom up in the way that Earth's ponds freeze from the surface down. It freezes from the bottom, and the ice that forms sinks away from the liquid, and the ocean persists. The physics of high-pressure water in a cold and distant moon works in a direction that preserves the liquid. Ganymede's ocean survives partly because of the unusual behavior of water under extreme pressure, and that unusual behavior is itself a product of the geometry of water molecules, a consequence of the angle at which two hydrogen atoms bond to an oxygen atom, and the way those molecules pack together when they crystallize under force. The angle is about 104 degrees. It is fixed by the shape of the electron orbitals around the oxygen atom. That angle and nothing else is why ordinary ice floats, and at pressures thousands of times greater than the surface of the Earth, water molecules pack differently. The angle becomes less relevant to the packing geometry, and the denser crystal sinks. The ocean under Ganymede's ice persists in part because of the angle of a chemical bond, measured in degrees, fixed by quantum mechanics, unchanged since the first water molecules formed in the early solar system from hydrogen and oxygen expelled by dying stars. The geometry of a molecule, held stable by the rules of physics, shapes the interior of the largest moon in the solar system across billions of years. Titan drifts on its far orbit around Saturn, its surface hidden beneath that permanent orange haze. The methane seas in the north, reflecting the dim, diffuse sky. The dune fields stretching dark and parallel across the equatorial plains. The river channels carved in water ice rock, draining toward the lowlands. The wind moves slowly through the dense atmosphere. The organic particles drift down from the sky and settle on the surface in a continuous slow accumulation that has been going on since Titan formed. The surface temperature is nearly 300 degrees below 0 Fahrenheit. The surface pressure is about 50% higher than at sea level on Earth, and somewhere between 50 and 100 miles below that surface, in a layer that has never been touched and may never be touched within any time frame that can be imagined now, the ammonia water ocean sits in its cold and silent dark, held liquid by the chemistry of ammonia and the slow decay of radioactive rock, pressing gently upward against the ice above it and gently downward against the rocky interior below, and doing so with no fanfare, no plumes, no visible sign, just the slow flexing of the moon's body under Saturn's gravitational reach that gives it away to instruments patient and precise enough to measure the difference between a solid moon and a moon with liquid inside. The hydrocarbon lakes at the surface and the water ammonia ocean below are separated by ice separated by chemistry, separated by temperature in opposite directions. The surface cold in one way, the interior cold in another, the interior warmer only relative to the ice around it, and warmer by a margin that would feel like deep cold by any measure familiar to a living thing on Earth. These are not warm places. None of the ocean worlds in the outer solar system are warm by any ordinary definition of the word. They are warm only relative to the freezing point of water, or warm relative to the temperature of deep space. The warmth that matters is measured in tens of degrees above the phase boundary, not in the comfortable range of the living things that evolved in the sun-warmed surface waters of a small rocky planet close to a yellow star. And yet, the living things that evolved in those sun-warmed surface waters also sent their representatives deep into the cold and dark. And what those representatives found there, in hydrothermal vents on the ocean floor, in the brine channels of Antarctic sea ice, in the water preserved in ancient subglacial lakes, sealed beneath miles of ice, was that life had been there long before they arrived. Not waiting for them, not aware of anything, just persisting, in the dark on chemical energy alone, in the cold, in the pressure, in the isolation, persisting because the physics of water and the chemistry of rock and the slow cycling of electrons through molecules is enough for what life requires, at the level where life reduces to chemistry, and chemistry reduces to physics, and physics has no preference for one configuration of atoms over another, except that some configurations persist and some do not. The outer solar system holds, by the best current count, several ocean worlds and possibly more that have not yet been adequately measured. Each of them formed in the cold region of the solar system where water ice was stable, and each of them was shaped by the specific mix of size and distance and gravity and radioactive heat and tidal force that its position in the solar system provided. No two of them are the same ocean. No two of them offer quite the same set of conditions. The range from Ganymede's isolated, ice-bracketed, rock-free sea to Callisto's faint and ancient brine to Titan's cold ammonia solution to the warm, hydrogen-rich, mineral-exchanging oceans implied for the most active of the ice-covered moons represents a sampling of the possibilities available in just one solar system among the hundreds of billions that exist in this galaxy alone. If ocean worlds are common, and the physics that produces them requires only ice and a source of heat and a body large enough to retain them, then the number of hidden seas in the galaxy is very large, and most of them are dark and cold and old, and have been there for longer than the Earth has existed, sitting in their ice containers at the edges of their solar systems, unknown and silent, and possibly, in some of them, not entirely still. The auroral bands of Ganymede shift back and forth on their 10-hour rhythm. They have been doing this since Ganymede formed. They will continue doing this long after any instrument built by any living thing has ceased to function. The ocean below dampens their motion, holding the swing to 2 degrees, pressing back gently against the sweep of Jupiter's field with its own quiet conductivity. The ocean does not know this. The physics does not require it to. The electromagnetic response is automatic, a consequence of the properties of conducting fluid in a time-varying field, as reliable and unintentional as the way a tuning fork responds to its matching pitch. The ocean replies. Jupiter's field sweeps on. The auroral bands rock by 2 degrees and not 6, and in that quiet shortfall, in that gap between prediction and observation, an entire hidden sea makes itself known to the universe, or at least to the brief and curious things living on a small warm planet that happen to build a telescope and point it at the right moon at the right time. Titan continues on its 16-day orbit around Saturn, and the methane rain falls on the northern seas, and the organic chemistry accumulates in the dunes, and the deep ammonia ocean sits in its cold, sealed interior, far below the surface, and the whole moon drifts through the outer solar system, wrapped in its thick orange haze, carrying its two liquid worlds, one above the other in the dark. As it has done for 4 billion years, and as it will continue to do, long and slow and vast and old, in the cold light of the distant sun. In the winter of 1977, the research vessel Cunora was positioned above a section of the Pacific seafloor where two plates of the Earth's crust pull slowly apart. The submersible Alvin descended from it in the early hours of the morning, dropping through water that grew darker and colder with every few hundred feet of depth, the light from the surface fading first to deep blue and then to nothing at all. 3 scientists sat inside a metal sphere smaller than a garden shed, watching through thick portholes as the black water pressed in around them. The seafloor, when it came, appeared first as a faint gray smear in the downward-facing lights, then as individual features, cracked basalt, pale sediment, the uneven terrain of a world that had never felt sunlight. What they found there had no place in the understanding of biology that existed the morning they left the surface. Clustered around cracks in the seafloor rock, where warm water seeped upward through the crust in slow mineral-laden currents, were animals. There were tube worms rising nearly 8 feet from the rock, their red plumes extending into the warm water like the fingers of hands held open. There were white crabs moving between them, and pale clams packed so densely around the vent openings that the basalt beneath them was barely visible. The water flowing from the vents smelled of sulfur, a faint chemical trace of the planet's interior, rising into an ocean that had been cold and still since before the first fish swam. None of it was supposed to be there. The sun had not driven any of it. No photosynthesis reached 2.5 kilometers below the surface, where the pressure is the weight of 250 atmospheres, and the temperature of the surrounding water holds steady near freezing. The animals were living on chemistry instead, on the energy released when hydrogen sulfide from the vents was oxidized by bacteria, the bacteria feeding the tube worms and the crabs and the clams in a food web with no connection at all to the surface world above. It was the first confirmed ecosystem on Earth built entirely without sunlight. And in the decades that followed, the picture it opened was not limited to the deep floor of the Pacific. It pointed, in time, all the way to the outer planets. The question the Alvin scientists brought back up with them was quiet but persistent. If life on Earth could build an entire world in the dark, entirely from the chemistry of rock and water and heat, what did that mean for any other place in the solar system where rock and water and heat might also meet? The answer would take decades to begin assembling. It would require spacecraft, instruments no larger than a briefcase, and data transmitted across hundreds of millions of miles of empty space. It would rest on the same basic principle that the tube worms demonstrated without knowing it in the warm dark of the Galapagos Rift, that sunlight is not the only way. The metabolism the vent bacteria use is called chemolithotrophy. The word is long, but the process is simple in its logic. If where animals like the ones breathing air at the surface use oxygen to oxidize food molecules and capture the energy of that reaction, the bacteria in the vent communities oxidize inorganic compounds instead: hydrogen sulfide, molecular hydrogen, iron ammonia, and pull the energy from those reactions the same way. No organic food needs to exist before them. No sunlight needs to have made it. The rock itself and the water seeping through it and the heat that drives that seeping provide everything the chain requires. The bacteria at the bottom of the vent community are the producers, and they need nothing from the star 93 million miles away. At certain vent sites on Earth's ocean floor, the chemistry runs even more quietly than at the high-temperature sulfide vents. Near the mid-Atlantic ridge, there is a field of pale spire-like structures rising from the seafloor, some of them 200 feet tall, their surfaces the color of old bone. The water seeping through them is warm rather than scalding, and the reaction that warms it is not volcanic heat, but chemistry. A slow reaction between cold seawater and the iron and magnesium-rich rocks below, a process that produces heat and releases molecular hydrogen as a byproduct. The field is called Lost City. The water flowing through it is alkaline, almost like weak baking soda, and the hydrogen it releases supports communities of microbes that consume it and exhale methane. Among the kinds of organisms on Earth most closely related to what life may once have looked like in its earliest form, the methane-producing microbes of Lost City are a serious candidate. They are simple, very old, tolerant of alkaline conditions and modest warmth, and they require nothing but hydrogen, carbon dioxide, and a compatible temperature to grow. What makes Lost City significant in the context of the outer planets is not merely its age or its simplicity, but its chemistry, because the conditions it describes, alkaline water, warm rock, molecular hydrogen rising from serpentinization, appear to be replicated to a striking degree in an ocean hidden beneath the ice of a small moon less than 1/300th the diameter of Jupiter. The match is not perfect. It may not mean what it appears to mean, but the similarity is close enough that astrobiologists have placed it at the center of their thinking about where in the solar system life might plausibly exist. And it is the reason that one small, bright, geyser-driven moon has become the subject of one of the most carefully designed missions in the history of planetary science. The concept of a biosignature is older than space exploration, but the precision of what it means has sharpened considerably in the decades since spacecraft began returning chemical data from other worlds. A biosignature is not merely the presence of organic molecules. Carbon-based chemistry arises without biology in many environments, and the outer solar system is full of it. A biosignature is a pattern that biology creates and that abiotic chemistry, as far as is understood, does not. The most reliable are several. One is isotopic fractionation in carbon compounds. Living organisms preferentially incorporate the lighter carbon, 12 isotope, into their tissues, leaving behind a measurable depletion in the heavier carbon-13. And the ratio of these two isotopes in organic material is a record of whether a biological process was involved in making it. Another is homochirality, the property of amino acids and sugars that describes their spatial geometry. In chemistry, the same molecule can be assembled in two mirror image forms, and abiotic processes tend to produce them in roughly equal proportions. But life, at least life on Earth, selects exclusively one form. All the amino acids and all the proteins in all living things on Earth are left-handed. If samples from an ocean world were found to contain amino acids predominantly of one mirror orientation, the simplest explanation would not be chemistry, it would be biology. A third class of biosignature is structural complexity of a specific kind, not merely the presence of large organic molecules, but the presence of molecules that carry encoded information, that are built in sequences too specific and too functionally organized to have arisen by chance from abiotic reactions. DNA and RNA are the most familiar examples, but the category is broader than those specific molecules. Any long polymer with a non-random sequence of subunits performing a function would qualify. The threshold between chemistry and life may ultimately be defined by this, not what the molecules are made of, but whether they contain information and whether that information does something. No instrument yet sent to another world has been designed to answer that question directly. The ones being planned for the next generation of ocean world missions are beginning to approach it. On Earth, the most complete available picture of what microbial life looks like in a cold, dark, isolated ocean comes not from any vent community, but from a lake that has been sealed from the surface for somewhere between 15 and 25 million years. Lake Vostok lies beneath nearly 2.5 miles of Antarctic ice in a basin shaped by the slow pressing weight of the glacier above it. The ice above it insulates the water, and the geothermal heat from below keeps it liquid. A thin layer of fresh water squeezed between rock and ice in a darkness so complete that no light has penetrated since before the first members of the genus Homo existed. The lake is not small. It covers an area roughly the size of Lake Ontario, and it is over 3,000 feet deep in places. It is one of the largest lakes on Earth, and until relatively recently, most scientists assumed it was essentially sterile. Analyses of the ice cores drilled above it told a different story. The lowest sections of those cores, where the ice has refrozen from lake water, carry within them the DNA signatures of microorganisms, traces of chemolethotrophs, organisms that metabolize sulfur compounds, and others adapted to conditions of extreme cold and near zero nutrients. The lake has not been directly sampled in ways that meet the strictest standards for contamination control, and the picture of its microbiology is still being assembled carefully. What the ice cores suggest, with appropriate caution, is that isolated liquid water beneath ice, cut off from sunlight and from the surface world, can sustain microbial communities over geological time. The processes that sustain them are slow. The nutrients are sparse. The conditions are close to the minimum that any known life can tolerate, and the life persists. There is something important in the word sparse. The life in environments like Lake Vostok or in the deep alkaline waters around Lost City is not abundant in the way the surface world is abundant. It does not fill its environment with biomass. It exists at the edge of what is chemically possible, taking what the rock provides, growing slowly, dividing rarely, lasting a very long time. This is the template that most astrobiologists carry with them when they think about the possibility of life in the oceans of the outer solar system, not the image of an alien sea teeming with strange creatures, but the quieter image of microorganisms in dark water near a warm vent, metabolizing hydrogen, producing methane, leaving behind a faint chemical trace in the water around them. Small, slow, persistent. The instruments that might detect that trace are already under construction. The science of mass spectrometry has advanced considerably since the first generation of spacecraft instruments flew through the outer planets, and the mass spectrometers being designed for the next wave of ocean world missions carry resolutions sensitive enough to distinguish not merely the presence of organic molecules, but their isotopic composition, their chirality in some configurations, and the masses of complex polymers that would distinguish biologically derived material from the abiotic organic chemistry that pervades the solar system. A well-designed mass spectrometer passing through a plume of ejected ocean water could, in a few minutes of flight, perform the chemical analysis needed to place limits on whether biology is operating in the water below. Not a definitive answer necessarily. Science rarely delivers those cleanly, and the interpretation of any chemical data from another world would require care and time and the willingness to consider alternatives, but a limit, a boundary on the space of possible answers that over successive flybys and successive analyses would narrow. The picture that assembles slowly from measurements like these is what the next phase of ocean world exploration is being built around. Scientists working on mission design for the coming decades use the word habitability with care. It refers not to whether a place is inhabited, but to whether it possesses the conditions under which life, as it is understood, could in principle exist. Those conditions distilled from everything learned from Earth's vent communities, its subglacial lakes, its deep crustal microorganisms, reduced to three: liquid water, a source of chemical energy; organic molecules in sufficient complexity to serve as building blocks. All three of these appear to be present in the ocean of at least one small moon. That is what makes the plumes that rise from its south pole more than a geological spectacle. They are a sampling mechanism. They are the ocean offering up its contents to the space above and to any instrument that passes through. The 2023 Planetary Science Decadal Survey, the 10-year planning document that guides American space science priorities, placed an Enceladus orbiter and lander among the 3 highest priority flagship missions of the decade. The vision it describes involves a spacecraft entering orbit around this small moon, spending years accumulating plume samples and surface data, and eventually delivering a lander to the ice, a lander equipped with mass spectrometers, microscopes, and biosignature-targeted chemical analyzers designed to determine, with the greatest possible rigor, whether the ocean below contains life or the absence of it. The planetary protection standards for such a mission are among the strictest in spaceflight history. The surfaces of any spacecraft component that might contact a potentially habitable environment must carry fewer than 300 microbial spores per square meter, a level of cleanliness that requires facility-wide sterilization procedures and materials testing, extending across years of preparation. The care is proportional to the question. Planning missions to the outer solar system requires a patience that is difficult to hold on to in an ordinary human scale of time. The journey from Earth to the moons of Saturn takes approximately 7 years, and a spacecraft in development today may not launch until the late 2030s, which means it would arrive, at the earliest, sometime near the middle of the 2040s, over 60 years after Alvin descended to the Galapagos Rift and found the tube worms waiting in the dark. The people who designed those early vent studies are mostly retired now or gone. The students who were inspired by the questions they opened have spent their careers building toward missions they may or may not live to see return data. Science at this scale has its own kind of time, neither geological nor human, but something in between, the time of a long and careful conversation that a community holds across generations, each person adding one sentence before passing the paper on. There is something restful in this, if it is held correctly. The answers are not overdue. The ocean has been there for perhaps 4 billion years, and it will be there for a long time after the spacecraft arrive. The ice does not thin. The vents, if they exist, do not go quiet between visits. The chemistry proceeds at its own pace, indifferent to human curiosity, governed entirely by the slow grinding of orbital mechanics and the steady liberation of heat from the moon's rocky interior. The spacecraft, when it comes, will arrive into a system that has been running the same processes since long before the Earth had continents. There is no urgency on the ocean side, only on ours. The image of a mass spectrometer counting molecules one by one in the vacuum of space, drawing a chemical signature from material that rose from a sea floor kilometers below the surface, and traveled upward through an ocean, through an ice shell, into the void. That image holds something worth resting beside. It describes a chain of events so unlikely, and at the same time so plainly physical, that it seems almost too direct. The ocean erupts into space. The spacecraft catches what the ocean throws. The instrument counts, and somewhere in those counts may be a ratio, a chirality, a molecular structure that resolves a question human beings have been carrying since long before they had instruments to answer it. Whether the life that arose in the warm, shallow water of an ancient Earth is unique to it, or whether it is simply what happens in the dark and the heat when water meets rock over sufficient time. No one knows. There are good ideas and real evidence pointing in multiple directions, and the plain truth is that this particular question is still fully open. That is not a failure. It is the current position of a very long investigation, carried out by generations of scientists and machines across distances that the human mind can name but not feel, into environments the human body could not survive in for a second. The investigation is ongoing. The next instrument is being assembled, and the ocean continues its slow work beneath the ice, unaware of the question being asked about it, generating its chemistry in darkness and warmth, as it has since before there were questions. There is an Antarctic ice core in a freezer somewhere, a cylinder of ancient ice cut from the deep layers above Vostok. If it is held to a light, the internal structure is visible. Small air bubbles, crystal boundaries, the faint milky texture of water that refroze from the lake below. Somewhere in its chemistry, there are traces of organisms that have been living in sealed cold water for longer than the genus Homo has existed. They are not waiting for anything. They are simply persisting, as life tends to persist at whatever margin is available, metabolizing slowly, dividing rarely, leaving their faint chemical signature in the water around them in the dark. The outer solar system holds, by current estimates, more liquid water than the surface of the Earth by a wide margin. Most of it is invisible, sealed under ice shells hundreds of kilometers deep, in the dark interiors of moons that receive less than 1/25 the sunlight that reaches Earth. The water has been there for a very long time. The heat that keeps it liquid comes from the slow grinding of orbital mechanics, the tidal flexing of moons caught between enormous gravitational fields, a process that has been running since the outer solar system assembled itself into its current configuration, and that will continue running for billions of years still to come. In that time, somewhere, in that dark, warm water, chemistry has been occurring. Whether it has crossed the threshold into biology is the question that the next generation of spacecraft is being built to ask. The threshold itself is not a sharp line. The boundary between complex chemistry and simple life is an area of deep uncertainty in biology, and the origin of life on Earth remains one of the most genuinely open questions in all of science. Several serious hypotheses describe plausible paths from chemistry to the first self-replicating molecules, and there is good evidence bearing on each of them, and no way yet to determine which path Earth's life actually took. The alkaline vent hypothesis places the origin at a site very much like Lost City, warm, hydrogen-rich alkaline water percolating through iron-rich rock, the mineral surfaces of the vent structures providing a scaffolding for the first chemistry complex, enough to copy itself. Other hypotheses place the origin in tide pools, in deep-sea sediments, in ice interfaces. Each makes predictions. Each has defenders. The honest position is that chemistry became life once on this planet, probably more than 3.5 billion years ago, and the record of how it happened has been so thoroughly overwritten by subsequent geological activity that the earliest chapters may be simply gone. What remains is not ignorance, but a set of well-bounded possibilities, and among those possibilities, the conditions in certain hidden seas are not excluded. The conditions at a low-temperature alkaline hydrothermal vent, in warm water slightly alkaline and rich in molecular hydrogen and carbon dioxide, in contact with iron-bearing rock, are among the conditions that the best current theories place close to the origin of life on Earth. This is not a guarantee of anything. It is a correspondence, one that the instruments of the next generation of missions are being built to investigate. The investigation will be slow, it will be careful, and it will be worth it, because the question it is designed to answer is the deepest one. In the dark below the ice of that small bright moon, water moves slowly over rock. The rock is warm, the water is alkaline and rich in dissolved minerals, carrying hydrogen upward in slow rising currents from the reactions occurring where ocean meets seafloor. Above the seafloor, the water column extends for tens of kilometers, quiet, cold in its upper reaches, warmer near the bottom, dark throughout. At the ice boundary far above, the pressure of the overlying shell has fractured the ice into long parallel gashes, and through those gashes the ocean vents its chemistry into space. Water vapor and hydrogen and methane and organic molecules and sometimes grains of silica formed in hot water at the seafloor, carried upward through kilometers of ocean and ice and finally released into the vacuum. The chain of events runs from the rock at the bottom to the instrument in a passing spacecraft at the top, and every link in it is physical and verifiable and slow. Whether anything in that chain is alive is the question that sits at the end of a long corridor of planetary science, still unanswered, still approached by one careful step at a time. The missions planned for the coming decades will place instruments in that corridor. They will not return a simple yes or no. Science does not work that way, and the interpretation of biosignature data from another world would require years of analysis and independent verification and the willingness to consider every alternative before reaching a conclusion. But they will narrow the space of possible answers. They will rule things out. They will establish limits. And if the data is consistent with life, the process of ruling out alternatives will begin, and the conversation will continue, as all scientific conversations do. Not with a sudden resolution, but with a slow and deepening clarity. There is a quality to this kind of inquiry that is worth resting inside for a moment, the quality of a question that has been asked across centuries and carried through generations, answered in small pieces, each piece altering the shape of the next question, the total understanding growing so slowly that no single person can feel it moving, but growing nonetheless. The ocean worlds of the outer solar system entered scientific awareness only within living memory. Within a single human lifetime, they moved from speculation to confirmed hypothesis to the primary target of the next 50 years of planetary science. That movement was not dramatic, in the way that historical moments are sometimes described as dramatic. It was a series of careful measurements, small papers, patient missions, instruments pointed at faint signals in rotating magnetic fields. It accumulated the way water accumulates in a deep basin, one molecule at a time, over a very long time, until the basin is full and the surface reflects the sky. The sky it reflects in this case is the question of life, whether life is common or rare, whether it arose once in a universe of billions of galaxies, or whether it arises wherever the conditions permit, whether the warm dark water beneath a distant moon carries within it anything that consumes and grows and divides and leaves behind a chemical record. These questions have been open for as long as human beings have looked at the sky and wondered what was there. They are closer to being answered now than they have ever been. They are still open. They will remain open for a while longer while the missions are built and launched and travel the long dark between the planets and begin their careful work. On the floor of the Pacific, in a narrow band of warm water rising from the spreading crust, the tube worms still extend their red plumes into the current. They do not require the sun. They do not require the surface world. They require only the chemistry of the rock below them and the water around them and the slow heat that drives the exchange between the two. They have been there in one form or another for a very long time, living at the edge of what is chemically possible, in the dark where no sunlight arrives, where the pressure of miles of ocean presses down from above. They are not aware of the questions their existence opened. They are simply there, the way life tends to simply be there, wherever the conditions permit it. The conditions in the outer solar system have been permitted for a long time. The water beneath the ice has been liquid, by the best current estimates, for hundreds of millions to several billion years. Time enough for chemistry to slowly accumulate complexity. Time enough for any early self-replicating molecule to have found successors. Time enough for the first metabolic pathway to have propagated through a population of cells, dividing once a month in cold, dark water near a warm rock. Whether any of that happened is not known. It may have happened, it may not have. The present state of knowledge is genuinely open, and the honest position is to hold that openness without filling it in either direction. What is known is this: the water is there, the heat is there, the chemistry is there. The ingredients are present in at least one hidden sea, in combinations that resemble, more closely than any other known environment beyond Earth, the conditions that gave rise to the only life that has ever been confirmed to exist. What the instruments will find when they arrive is still ahead, still unwritten, still unresolved, still drifting slowly toward the small bright moon across the years. Somewhere in the outer solar system, in the cold dark beyond the reach of ordinary sunlight, the geysers are still rising. They have been rising for longer than recorded history. They will be rising when the next spacecraft arrives. The material they carry moves upward from the seafloor through kilometers of dark, warm water, through cracks in the overlying ice, out into space, silica and salt and hydrogen and methane and complex organics, rising in pale curtains above the south pole of a small and ancient moon.